crazy world. And that is to say, you often are in situations where you need to write programs on data that is too big to fit in memory. Because normally the way you write a program is, you take in your input file, you load it all up into memory, and then you do whatever you need to it, and then write out the output. And this works really well when your data is relatively small. In fact, it works decently well when your data is fairly big and you have a beefy machine and you can just load it all into RAM. And I would say if you're working on an engineering problem and you can just stick everything in memory and then work on it, just go ahead and do that. It's very simple. But sometimes the data is too big, or maybe you just don't want to use that much memory, and you don't need to because you only need to process the data a little bit at a time. So you need some way to represent this concept of streaming where you don't do everything all at once. Instead, you handle chunks of data one at a time. There's a question in chat. Didn't we say that Haskell uses call by name as opposed to JavaScript in previous lectures? So lazy evaluation should be a different strategy apart from call by name and call by value. So if I said that Haskell is call by name, I apologize. I lied to you. Haskell is not call by name, and it's not call by name precisely because if it were actually call by name, we'd be obligated to reevaluate expressions every time they showed up in our programs. We'd be obligated to evaluate our arguments every time they were used. And that's not what Haskell does. Instead, Haskell evaluates it once when it's requested and then reuses that result later. But yes, lazy evaluation can be thought of as a different form of evaluation than call by name and call by value. It's a little tricky to model in only the lambda calculus, however, because the model lambda calculus doesn't really have a concept of sharing computed results. Call by name is a very syntactic thing, right? You just substitute in the expressions and then you keep going. Lazy evaluation, we need a more sophisticated representation of the program internal state. That representation is a graph, and that's why we're going to talk about graph evaluation later in this lecture. Okay, so big data can't fit in memory, want to process it as we go. And lazy evaluation gives us a very, very natural way of representing this sort of situation. And so instead of my previous example where I just had these big computations that I wanted to save for later, instead the thunk, the suspended computation, is going to represent the rest of my too big to load into memory stream that I can sort of poke at to get when I'm ready to process the next piece of element. But if I don't poke at it, if I'm just working on my earlier payloads, I don't actually need to materialize the stream just yet. And so Haskell makes it really, lazy evaluation built directly into Haskell makes it really, really easy to do programs with streams. Okay, monotonicity. What is monotonicity? So we're going to talk about races and concurrency more when we get to concurrency later in this class. But the essential problem of concurrent execution is suppose that you have two threads and they're both operating on some shared state, and they're both mutating, say, the shared state because they're doing operations. They need to write to memory their results, and we have a question, which is how do we prevent data races between thread 1 and 2? And normally the answer you would give in this situation is, well, let's do a lock. But with locks, it's kind of hard. We'll talk more about why it's kind of hard with locks. And it's also easy to accidentally forget to actually lock your things correctly and have data races. This is why tools like Thread Sanitizer exist, because it's too hard for our puny little brains to figure out how to write race-free code. So we need a lot of help doing it. And what better help is there to preventing data races than to make them entirely impossible to begin with? So Thunks, these suspended executions, can be a way to pass results between multiple threads without having any possibility for data races. And the way this works is that let's suppose I have one thread that is working on some result, some computation, and it wants to send it to another thread which actually wants to consume that result. Instead of like having some piece of shared memory which the producer writes into and then the consumer reads out of, what we can do instead is we can send a thunk over to the consumer. The thunk is, remember, a suspended computation. It's a promise on how to do the execution at some later point in time. And so instead of this thunk looks just like a normal piece of data, but if the consumer attempts to access the thunk, it will block because the producer is already working on filling out the data in that thunk. And you don't write your code any differently. To the consumer's perspective, the thunk just looks like a plain old normal value, but it will in fact wait until the producer produces the value. And it's not possible to race in this situation. There's a question in the chat, which is this sort of like promises in JavaScript? And the answer is yes. And we can basically do promises without writing our code any differently at all. Now, in Haskell, you might want to explicitly represent this sort of, cross-thread communication, and there are other abstractions for doing this. But for very simple cases, you can just use plain old values, and they will do the right thing. My last justification was functional programming. Now, there's another question, which is, if these are separate threads, the lock is hiding inside however you're sharing the thunks. And that is correct. There's not actually a lock, and we'll talk about this more in the implementation segment of this lecture. It's just, it can be done with, I guess it's a spin lock, but it's a very, very teeny lock, and the user doesn't have to see it at all. So my last motivation was functional programming. So what do I mean by functional programming? So this is sort of evoking a more general concept of programs written in Haskell, which we haven't really gotten a chance to do in this class, but is like if you wanted to keep writing Haskell, this is where I go next. So in functional programming, we love writing so-called domain-specific languages. What's this? So Haskell is all about raising the level of abstraction, right? When we came here and we had just written in imperative programming languages, we were used to saying, do this, then do that, then do that, right? Explicitly spelling out in excruciating detail every single thing we wanted our programs to do. And then Haskell said, well, you can just sort of write code as if it was kind of mathematical, and we'll figure out how to execute it for you. And that raised a level of abstraction because we focused more on saying what our programs should mean rather than what our programs should do. And DSL's taken another step up. They say, hey, if I want to write a parser, and that's what the example on this slide is about, if I want to write a parser, instead of having to write out, okay, first take out a character, look at the character, see if it's a comma. If it is, go to this token in the state machine, and so forth and so forth. Instead, what I want to do is I want to take a bunch of high-level programs describing the grammar of my application and put them together to form something that looks very much like a grammar, and then I can actually have abstractions that know how to turn this into a proper parser in the end. So these are parser combinators. There's a very famous library called Parsec, which first popularized them. There are a number of other parser combinator libraries in Haskell. And something interesting that happens when you want to write parser combinator style, and also parser combinators have made their way to other languages. But when you use them in other languages, they're not as nice. And why are they not as nice? Well, they're not as nice because whenever you're writing these combinators, you always have to insert all of these one-off functions. And why is that? It's because essentially you're writing this program, and the inside parts of the program shouldn't get executed unless you are actually at that point in time during the parsing in question. And in eagerly evaluated languages, you have to go ahead and evaluate all the arguments to your function immediately when you specify them. So you have to insert all these function blocks. But in Haskell, that's not necessary because Haskell is lazily evaluated. So I can just write code that takes in things as arguments. It looks very clean. There's none of these random extra functions that I need. And at the same time, Haskell won't go ahead and evaluate any of these until I actually need them. So the short version is, you don't have to write function, open paren, close paren, curly braces everywhere. Because Haskell's lazy, so you don't need that, because Haskell implicitly has done that for you everywhere you write in your program. But there's more to functional programming than just DSLs. So another really good thing about laziness is compositionality. So what's going on with compositionality? Well, here is a function called any. It takes a predicate and it takes a list and it returns a Boolean. So what does it say? It just says, if there's any element in this list that satisfies the predicate, then return true. Otherwise, return false. And I can implement this using a combination of two functions, map, which takes this predicate and applies it to every element on the list, and or, which takes the list and basically ORs all the results together. Now, in an imperative language, you wouldn't want to build any up this way. Why? It's because mapping the predicate over every element in the list is wasteful in the case that, maybe the first element satisfies the predicate. Well, then you only needed to check the first element, and then you could just go ahead and return immediately with true, right? So you'd want to actually write a loop out on your own. But in Haskell, the results produced by map are lazy. We don't actually bother computing the mapped out values of the rest of the list until we actually need them. And OR is short-circuiting, so OR will only consume as many elements from the list as needed until it finds a true. Then it'll stop and just immediately return true. And as a result, nothing after it will actually get mapped, because map was lazy and didn't do the operation until you requested it. Saying the same thing that I just said. One more thing. So any questions about this example? We'll return to this when we look at more at streams. One last thing in functional programming. So cyclic data structures are another important reason why lazy evaluation is important in Haskell. So this stems from a problem which is endemic to pure languages that don't allow side effects by default, which is that it's difficult to actually explicitly represent graphs. And let's just walk through a little example showing why. So let's say that we want to represent this graph that is below in Haskell. And so the way we're representing nodes is nodes are simply, data structure that contains a list of pointers to other nodes. So in this case, A has no outgoing pointers, so its list of edges is empty. And B has two outgoing edges to A and C, so I can define B and say A points to B has A as an edge and it has something as an edge. Well, I haven't defined C yet. So I could just say, okay, well, let's define C first, but C here has an edge back to B. And so there's no ordering I can do for these declarations that will actually give me the data structure in question. C needs to refer to B, B needs to refer to C. If I were in an imperative language, I would have just, allocated C with no edges, then allocated B, and then finally added B to the edges of C. But I can't do that in Haskell because Haskell is a pure language and mutation is not allowed. So with laziness, there's no problem. You can actually just write your let statement, put all the elements, refer to the things you want, and it will work. You may have actually accidentally written some bugs this way while you were coding Haskell, where Haskell lets you refer to the variable you were defining. So I won't claim that this is always what you want, but in this particular case, because once again, the values of the node B, A, and C are evaluated lazily, I can refer to B before I've even defined it, because I'm not going to actually need to execute it until later. And so now I can set up all these references in this case. Okay, so that's it for motivation. Any questions about anything? What are your questions about what we've done so far? Okay, let's do some details. So the core principle of lazy evaluation is we do not evaluate expressions until they are needed. And so the crux of the matter is, what does it actually mean to need something? So to look at this, let's look at some examples. So here I have two functions, f1 and f2. F1 is a function that takes in a maybe A and then returns a list with 2 copies of that maybe. And function 2 is a function that pattern matches on the maybe and returns an empty list if the maybe is nothing, and returns X, a singleton list with X if it's just. And really, we were talking about need, right? So the question here is, does F1 need the value of M? Does F2 need the value of M? Well, let's take a look. So in F1, we don't actually really need M, right? We use the argument. We do put it in a list, but we don't care what it actually is. We don't care if it's a just. We don't care if it's a nothing. If you pass me a pointer saying, hey, here's where maybe A is, I wouldn't even look at the pointer. I just shove the pointer into my return list in the situation. In contrast, F2 needs to know what M was. It needs to know if it was a nothing or a just X, because it's going to do something different depending on if it got nothing or if it got just X. So, hey, we need to know what M was to compute the result. We need to actually evaluate M in this situation. Note though, this X on the inside, we didn't need that, right? We're just putting it into the list, and maybe someone else will need it at some later point in time. So let's try and go ahead and actually evaluate the function f1 on some input. So to start off, this program has an IO action in it. And I'm going to sort of implicitly assume that I'm running this IO action as part of main. Why? It's because, we actually need to kick off the evaluation somehow. Because if you just have a Haskell program that's all pure functions, well, Haskell is more than happy to just not do anything, right? Because you didn't ask it to do anything. The only effect that programs have is, actually interacting with your environment. So to print, we need to actually see the value of the Boolean that it's passed. Null, in this case, is testing if the list is empty or not. So we're going to go ahead and evaluate the expression null f1m. So what are we doing here? So the implementation of null says, if the list is empty, then return true, otherwise return false. So I just go ahead and inlined null into this program. So case f1m, if it's empty, return true. If it's a list, return false. So now we see that to evaluate this expression any further, we need to evaluate more. We need, in particular, to evaluate f1m far enough so that we know if it's an empty list or not. So in other words, pattern matching drives evaluation. We don't bother doing any evaluation unless we are, at a point in time where to evaluate something, we need to evaluate a case statement. And in that case, we're going to go ahead and evaluate what we're casing over. So let's go ahead and evaluate f1m. So f1m returns a list of m, m. We did not evaluate m because there's no pattern match on it, right? The implementation of f1 just said take m, stick it into the list twice. So now we have case m, m of, and then some branches. Above in blue, I've drawn a box diagram of sort of what this value kind of looks like, right? So we got 2 list cells, and the first cell points to the thunk for m, and the second cell points to the thunk for m as well. So now we need to do the evaluation. So I rewrote the list in cons and nil forms, so it was more obvious what was going on. So list of two elements is m colon list. And we can see that, in fact, this expression has already been evaluated enough to do the case on, because we know that it's not an empty list, because we can see the cons in the result of F1. And so in the end, M is never evaluated. Questions so far? Okay, so let's go on and look at example 2. So once again, I've set things up the same way. I'm going to print, and I'm going to print null of f2 of m. Once again, when I print, that evaluates the Boolean returned by null. So I'm going to need to evaluate this expression. Go ahead and inline null. Once I've inline null, I see that to find out what the value of null is, I need to evaluate the case statement. So I'm going to go ahead and inline F2. And now we see that when in F2, remember F2 pattern matched on its argument to return either an empty list or a list of X. So now I want to run this case, and inside the thing I'm casing over, I have another case. And that means that I have to evaluate the inside of the case. So I'm going to evaluate M. Yeah, pattern matching causes evaluation of thunks. So the rule in general is that expressions are evaluated on pattern match, but only enough to make the match go through, right? I'll go ahead and evaluate, and if I figure out now, oh, I know what the case statement needs to go, then that's it. I'll stop evaluating and I'll just go ahead and do other things. And for what it's worth, we didn't have any examples of like adding things or subtracting things, but primitive operations like those also pattern match their inputs, because you can't compute what the sum of 3 and 4 is without actually knowing that you were doing a sum over 3 and 4. Questions? Crystal clear? All right, well, let's do another example then. So I talked about any, and let's try this out on a kind of interesting use case. So here I want to print if there is any element in the infinite list. This is in fact an infinite list. If I say 0 ... that'll give me 0, 1, 2, 3, 4, 5, 6, and so forth and so forth. Remember, Haskell lists are streams. They can be infinite in length. We won't actually evaluate them until you need them. And we want to print if any of these are greater than 1. Now, intuitively, the answer to this should be true, because once we get to 2 in the infinite list, we will realize, hey, there is a element that is greater than 1, and we should just immediately return true. We should not try to evaluate everything in the infinite list. That'll just, infinite loop in that situation. So how do we actually get here? Let's see. So first I print. To print, I need to evaluate any to get out a Boolean. Let's go ahead and inline any. We implemented any as a map and then an or. I got rid of the dot, so it's just or is applied to map greater than 1 and 0. We need to evaluate or, so we're going to go ahead and inline or. So just a reminder of how OR is implemented. The way OR works, right, is it takes in a list. If the list is empty, then nothing is there and we just return false. If the list is not empty and the first element is true, then we're done. We don't need to do anything else and we just return true. And otherwise, we need to keep going looking for a true in the rest of the list. Everything else is the same. I didn't modify map. But now we can see that we're trying to evaluate a case, and evaluating a case means that we need to evaluate the inside of a function. So evaluate that we will. So let's inline map. So how does map work, right? Well, map just says, give me a list. If it's empty, return the empty list. Otherwise, run the function over the first element of the list and then recursively map the rest of the list. So that's what I've inlined here. And once again, we have another case. So we need to evaluate the inside of this function. And now we're getting to an interesting bit, right? So 0 dot dot is a thunk that represents the list 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. But we don't actually need to evaluate all of it. We just need to evaluate enough so that this case goes through. So all we need to know is if it's empty or not. And that's really it. So we will evaluate it just so that we can figure out what is going on with the first cell. So in blue, I've done a little diagram. We have a single list node. That's all we needed to do the case statement. And the first part of it points to 0, and the rest of it points to a thunk representing basically an infinite list starting at 1 this time rather than 0. So now I have enough to go ahead and do the case. So we see it's not empty, so therefore I want to go and do the non-empty case. So let's go ahead and substitute everything in. So we have x is greater than or equal to 1, colon, map greater than or equal to 1, x's. And x in this case is 0, and x's in this case points to that thunk that represents the infinite list starting at 1. And so now that we've returned this, we can actually make progress on the outer case as well. Because, hey, we've got this list, so we know that it's definitely not an empty list. So we go ahead and want to try doing the rest of the case statement. And once again, we need to actually do some more computation because this case statement needs to know if the first element of the list is true or false. And remember, we were lazy, so we didn't even actually bother evaluating the greater than or equal to 1 statement. We just said, okay, we're waiting. And now we need it, and we're going to go ahead and evaluate it, and it's false, refuting the true case here. So now there's only one more pattern match left, and we are going to end up with or rest, where rest points at the map greater than or equal to 1 on the infinite list starting at 1. So this looks a lot like what we started with, but there's a slight difference, right? The slight difference here is we're not running OR on map of 0 to infinity. We're running OR of map on 1 to infinity. So we can, and importantly, we didn't evaluate any of the 1 to infinity because we didn't need to. We only needed to look at the first element to figure out what was going on. So once again, so we can go ahead and run this again, but instead what I've done in this slide is I've laid it all out, what actually gets evaluated in the end. So on the left-hand side of this slide, we ran OR on map of greater than or equal to 1 on the infinite list 0 dot dot. So here first, what we did was we, okay, so what we did in the slides before, right, where we said, okay, to find out OR, I need to know the map. To find out the map, I need to know the list. So I get a 0, and then when I map over it, is 0 greater than or equal to 1? No, so that's false. And then I find out, okay, well, I need to go do it again on the tail of the list. Then on the tail of the list, I go, I get out 1. I run, is 1 greater than or equal to 1? The answer is true. And now, in that pattern match, I get true, and that just says, okay, I can just go ahead and return true in this case. And I never bothered evaluating the infinite stream starting at 2, nor did I bother evaluating the map on that infinite stream starting at 2. There's a question: when does Haskell reuse the result of a thunk, and when does it make a second thunk and evaluate again? As a first guess, I'd say it reuses if the result is bound to a name, for example, passed to a lambda, and evaluates it again if you call the function twice in a list. Are there less obvious examples, or am I wrong? This is a great question. So in general, sorry, let me think. I don't want to say in general. Naively, Haskell will only evaluate a expression once if you actually shared it. So if you said something like let x equal fa, and then you used x a bunch of times, then you would only evaluate f of a once, and then it would get reused everywhere, right? So there's a thunk because you gave a name to this intermediate expression and then used it multiple times. And if you used f of a itself, that expression multiple times, then there wouldn't be any sharing necessarily. But this is the naive formulation, because one of the reasons why Haskell works at all is because it has a very aggressive optimizer that is willing to do a lot of code transformations. And there are in fact 2 code transformations it could do that cause this reasoning here to not work out. So the first optimization it can do is it can inline. If it sees x equals f of a, and it knows f of a is very simple and not a big deal to reevaluate, it may just go ahead and replace all your occurrences of x with duplicated copies of f of a. And this can be profitable because if Haskell happens to know f of a is actually just true, then by propagating true to all of the use sites, it might be able to unlock more optimizations where we can further simplify the code in that question. So inlining can cause a expression to not get bound to a thunk, but instead just go away entirely. Conversely, there's an optimization called common subexpression elimination. What that says is if I have 2 occurrences of the same subexpression, like in your example, f of a and f of a, your compiler is allowed to turn these into a single shared binding and use that result in both places. Now, this can be a not so great optimization, in particular if the arguments to this function are very expensive and only one of them gets used. If the result of the function is very expensive, it might not be a good idea to keep holding onto it while you wait for the second thunk to actually use it. So I don't think, once again, this optimization is not enabled by default, except when the compiler can prove that there is no harm in doing it. And there's like an f-full laziness, I think, flag that lets you turn it on if you want that optimization. There's a meta point, though, that I want to make, which is that the observable behavior of your program, unsafe perform IO notwithstanding, will always be the same, because remember, Haskell's pure and we can't actually see when things get evaluated. So and in particular, when we look at this model, the only way we can actually observe if something is lazy or not is, via the performance characteristics. And Haskell will preserve the performance characteristics when it does these optimizations, or at least for the optimizations it does by default. Well, or make your code run faster, because that's always okay for an optimizer to do. Nice question. Okay, so this example using map and or is actually a example of a more general phenomenon in Haskell called stream combinators. So here are a bunch of functions that we've seen already in the standard library and on your homeworks, and we also talked about some of them and implemented some of them. And the amazing thing about all these functions is they are all lazy. They all work on infinite streams. They all only do as much work as is necessary to actually operate on them. There's one function that I want to talk about in particular, and that's foldr. So let's take a look at this. So a while back, I think I attempted to explain folds a little. Usually it's a little hard to explain what's going on with all the different fold variations until we've talked about what lazy evaluation is. So finally we've got it here, and I can actually give you a proper explanation of what's going on with all the folds. So foldr, if you don't recall, was a way of sort of generically transforming a list. And I actually think FOLDR is pretty easy to understand. The intuition behind it is, let's say we have some list, right? We have a list of two elements, A and B. When we visualize this list as a data structure, we have these con cells and we have the nil cells. So, the con cell contains an A and it contains the rest of the list, which is a con cell containing B and then an empty list. And we looked at a bunch of different, types of operations like summing all the elements of a list together or multiplying all the elements of the list together. And so folding generalizes this concept to say, well, you can always fold by doing some arbitrary binary combining operation, that's F, and some arbitrary empty element, Z, which you're going to put in in place of the empty list in question. So literally what you're doing is you're taking this abstract syntax tree representing the list itself, or the data structure representing the list, and replacing the conses with F and the empty list with a Z. And this gives you a call graph representing the computation that you want to do on this list. Pausing a moment. Okay, so when I say folder FZAB, that's equivalent to saying compute FA open paren FBZ close paren. Okay, so let's take a look at this. So let's say that we want to actually evaluate this because maybe we printed out the result of this operation. So we're trying to evaluate this expression, this thunk that is F. And a question we have in our heads is, do we need to evaluate A? Do we need to evaluate the right subtree? And in general, we don't know because it depends on F, right? What we're going to do is when we do this evaluation, we'll inline F and we'll see what the insights of F are. If F just always returns true, then I don't need to evaluate A and I don't need to evaluate the right subtree. I can just return immediately. Or if it returns A, then I can just return A. Or if it looks at A and, does a case on it and then doesn't look at the right subtree, I only need to look at A in that case. I don't know. I need to know what the implementation of F is in this situation. So for example, we can implement maps as a fold R. And the way that I do this is I'll define F to be, well, give me an X, give me an X's, and I'll just make a new console between G of X, having applied the G of X, and then whatever the right subtree is, which is what you modified on the right-hand side. And then Z will just be an empty list. And with this function F, in fact, we will not evaluate the left-hand side or the right-hand side of the list if you just peek at whether or not something's a con cell or not, because there's no need to. You didn't actually need to run any of those computations just to find out if the list was empty or not. Questions? What are your questions? So this is a fine way to implement map. Totally okay. Here's another example. So filter was the function that took in some predicate and returned only the elements that satisfy that predicate. And so, we can once again implement this with fold R. What do we say? Well, we say, okay, give me my element. If that element is satisfies the predicate, then I'll return X plus, whatever the rest of the right subtree I did when I filtered it. Otherwise, I'm just going to return the right subtree. And Z, once again, is the empty list. And now in this case, there might be a lot of evaluation going on when you ask for the first element of the if you ask whether or not the result of the filter is empty or not, right? Because if your filter actually doesn't ever trigger on any of the elements, you actually need to zip all the way to the end of the tree to find out, no, in fact, there is nothing that satisfies this filter, and I'm going to give you the empty list. So not only is this, dependent on our choice of F, but it can be dependent on the data in question as well. And of course, we always have to evaluate, So there's a question on the slide. It's a trick question, which is, in this example, did I evaluate A? Any takers? It's a trick question. Depends. So we do evaluate P of A because we need to know if it's true or false to find out if the conditional goes to the first branch or the second branch. But indeed, it depends, because if P doesn't actually look at its argument at all, then whatever, right? Like, it could be the constant filter which returns everything, and then there's no need to actually evaluate the elements. So yeah, it really, really depends. So this is one of the reasons why it's kind of hard sometimes to reason about laziness, because you really need to like know what the functions are doing to see what they need or not. This is another example, but I'm just going to skip this example. Maybe we can come back to it if we're interested as it. Okay, so there's another question. I've heard of tail call optimization that takes into account cons. The laziness removes the need for that and works for other such functions, constructors as well. Does GHC try to do clever things anyway? This is a great question. Okay. So the first answer is Haskell does have tail call optimization. If you don't know what tail call optimization is, don't worry. We're about to talk about it in like 3 lectures. So we'll talk about it in more detail. However, we don't need tail call optimization, and it doesn't apply in the case of map. And why doesn't it apply in the case of map? That's because, it's not a tail call, right? You're not, you're going to first, whatever the thing is that, the words are getting away from me. The recursive call to map the right subtree of your list, the tail of your list is not in tail position because you need to put it inside a console. But it doesn't matter. You're not going to Stack Overflow because we don't bother doing it. We're lazy, and we're just not going to actually bother doing the map on the rest of the list until you actually ask for it. So although this looks like it could Stack Overflow, it does not in Haskell because Haskell is lazy. In contrast, in OCaml, they define all of their maps, and they have to be careful, because if they define their map in the same way Haskell defines their maps, they will in fact Stack Overflow because they have to push a stack frame for every single element. So what you'll typically see in OCaml is you'll see it very soon. They'll do a full val and then reverse the result to get it in the right order. That being said, not everything is all well in Haskell. And so this example for sum is an important example. So let's see if we can use fulldar to re-implement sum, which takes all of the elements of a list and sums them together. So here's a very simple implementation. I just take my left subtree, my right subtree, and I say, okay, I just want to add them together, right? So I'm going to replace all the colons with pluses, and I'm going to replace the z with 0. And so this seems pretty reasonable. Like in this situation, I need to evaluate both the left-hand side and the right-hand side because, hey, plus is a primitive and it needs to know both of these things to do the evaluation. But if I have a very long list, my call tree looks like this. And just like what I was just sort of ragging on OCaml for doing, we need a lot of stack to actually evaluate this. And so if you actually try to use folder to evaluate the sum of a very large list, you'll get a Stack Overflow in this situation. And this is why we have this is why folds on lists are very complicated in Haskell. And you probably already know a bunch of downsides to lazy evaluation, but this is also another one of them, which is you have to be very, very careful not to accidentally blow your stack. So what's going on here? So fulldar is great if the result of the function is itself a lazy data structure. because full-dar preserves laziness. It only goes ahead and evaluates as much as you need, right? And so that was why we could use it to implement map and filter, and those all worked pretty great. But if you try to do a sum, it will Stack Overflow because it will generate this entire lazy computation and then try to recursively execute the inside. And we have to evaluate all the way on the inside before we can go evaluate the outside. So to solve this problem, we need to flip things around. We need to stop building up this large stack of deferred operations, plus 3s and plus 2s. We want to use an accumulator. And this is what fold L does. So fold L basically flips it around. So instead of executing the list as if it were a right biased tree, it instead says, okay, well, we're first going to go and evaluate on the first element with some item, and that will give us an intermediate result. And then we'll just successfully add things onto the intermediate result as we go, building up our accumulator until we get the final result. And so unlike the previous situation where I need to first evaluate the inside and then and only then can I start peeling off the plus 3, plus 2, plus 1. Here, because I have my 0 and I immediately start accumulating into it, I don't need to do that. Of course, that all sounds all very nice and good, but this function doesn't work either. It also stacks overflows. Why is that? Well, the problem is fold L does have an accumulator, but it's also lazy. So this accumulator, right? Fold L doesn't need it. It doesn't actually need to use the result. It can actually defer the computation. And so what actually happens is when you fold L in the situation, it just keeps building up a big chain of thunks for all the operations you need to do, because hey, you didn't tell fold L that it needed to do anything special. It's just going ahead and delaying the computation until later. And so when you actually execute this stack of, once again, deferred pluses, you'll once again Stack Overflow because we once again need to zoom down to the inside and then do them out. So to actually get there, we need to make sure that we evaluate as we go. And in Haskell, there is another function, foldL prime. The prime here just means the function is strict. And finally, we can write a sum that actually works and doesn't Stack Overflow. Phew. What are your questions? So the high-level takeaway is that, lazy evaluation is cool and it saves you a lot of work, but it's not a good idea sometimes because you don't want to defer too much computation, right? It's very similar to like when you're lazy and you don't want to do your homework and then your homework piles up and then you have too much homework and it's terrible. And if only you had done a little bit of homework every day up until the deadlines, then it would have been much more manageable. Haskell's like that too. If you give it too much piled up homework, it will Stack Overflow. So it's better when you know that it is profitable to gradually do evaluation along the way. There's a question, which is fold-R prime doesn't make sense because lists are lazy. That's a good question. So we just need to look at our fold-R diagram. So there's a problem, which is that I'd like to go ahead and immediately evaluate this. But to do that, I need to evaluate the right subtree, right? Because it's not like the fold L situation where I started off with the 0 element and then I started adding things into it. I don't know what the value on the right hand side is. So that's why there's no fold-R prime. Okay. Any more questions? All right, let's move on to the bonus segment for this lecture. So I said I was going to tell you how thunks are implemented in Haskell. Where is that hidden lock, as was asked in the questions? And so the way that thunks are represented in Haskell under the hood is they're a data structure. So there's a header on the data structure. This is very common when you are working in so-called boxed language runtimes. Java is similar, where you have all these objects in your system, and they always have some sort of description at their top saying what kind of object this is. And it's important to have that description because without it, you can't write code that can take in arbitrary types of objects. And so in this particular case, there's a specific label that identifies that this is indeed a thunk. And in fact, in Haskell, this is literally a functional, in GHC Haskell, this is literally a function pointer which contains the implementation of the suspended commutation for the thunk in question. And of course, to actually execute this, there might be some data that was closed over by the expression, right? Like if our thunk is f of x, well, x needs to be saved so that we can actually evaluate it later. And so there's some payload that represents the rest of the data that I need in this situation. Now there's one field in the data structure that is reserved, and we'll see how that is used in a moment. There's a question in the chat, which is how do thunks relate to the idea of continuation passing or callbacks? And the answer is they're not too related. One connection you could make is that let's say that you are executing and you hit a thunk, and that thunk is being worked on by another thread. You will basically get suspended and you'll get called back at some later point in time when the value for that thunk is available. So it's a sort of simple form of callbacks that you don't have to do anything special to do. It'll automatically happen in Haskell. But we'll talk about continuations in control flow. Also in a few lectures, very soon, actually. So let's say what happens when we evaluate one of these thunks. So when we evaluate this thunk, we go ahead and do the computation associated with a function, and that gives us some new result. And typically that result is just going to live somewhere else on the heap because there was just some other function responsible for doing all the work. It has no idea that it was saved in a thunk, and it's just going to go ahead and do all sorts of computation until it has allocated its final result object on the heap. And also in general, the thunk may not be big enough to store the entirety of the result. So that result is just going to go out and hang out somewhere else on the heap. And then what we do is we atomically replace that reserve space with a pointer to the result, and then we flip the header from saying that this is a thunk, aka you have to go and evaluate it to get the value, into an indirection, which says, hey, there's nothing to see here. Your princess is in another castle. In this case, your result is in another location on the heap. And you can just go ahead and look at this word to see it. And this doesn't require any locks. There's no actual explicit locking that happens. All you need is an atomic memory write into the indirection, and then an atomic memory write on the tag of the table in question. And now all the other threads will now see that it's an indirection now, and the indirection field will be already set up because you had memory ordering between these two atomic instructions. So there's a question, which is, could there be a race condition where you run the thunk twice? And the answer is yes, there is a race condition. So if you are working on a thunk and someone else says, hey, I need that thunk, by default, Haskell is okay with duplicating the work. And this is actually fine because in Haskell, all of the thunk computation is side effect free. So it doesn't really matter if you execute it multiple times. But if the computation is very expensive, it might be bad for performance to repeatedly be redoing the same computation because a lot of threads raced on it. And so there's an option in GHC Haskell called eager black holing, which says that when you start evaluating a thunk, you can atomically swap this thunk with a black hole header. And the black hole header says, hey, someone else is working on this thunk. Please wait until we get back to you. And that closes up the race condition. And actually, in some situations, we will black hole anyway. In particular, if we're evaluating a thunk and it seems to be taking too long and we context switch away from this evaluation, by default, Haskell will then go ahead and write in this black hole header. So eager black holing just says it's completely unacceptable to race at all when we are working on this. And then if someone else sees a black hole, now they know, okay, I just need to suspend myself and wait for the computation to come back. There's a question, which is all Thunk commutation side effect free though? What do the inlining, etc. optimizations mean for functions that do I/O? Or does I/O constrain or complicate things enough that these optimizations are usually not allowed to happen? I guess we've encountered laziness making I/O run in strange orders, so we know that happens. Does laziness mean the evaluation order depends on specifics of how GHC transforms and optimizes various expressions? Does Haskell have a way to guarantee the ordering of certain operations? This is also a great question. I have time, so let me just go ahead and answer this. So the answer is no. Not all Thunk computation is side effect free, right? And in fact, unsafe perform IO is precisely an example of a way to stash an arbitrary side effect into the computation. But there is a catch. Unsafe perform IO is operating under the sort of like naive model where, when you write expressions, they turn into thunks, and, there's no such thing as inlining or common subexpression elimination. So if you can run the internal, graph evaluation model in your head, that tells you when the unsafe perform IO happens. And in practice, this is basically true. And why is this true? It's because unsafe perform IO is special cased in the runtime. When I start evaluating an unsafe perform IO thunk, regardless of whether or not I opted into eager black holing, I always black hole the unsafe perform IO thunk. So we actually do take some measures at performance cost to make sure that unsafe perform IO blocks only get evaluated once. And there's similar inhibitions in the optimizer. So the optimizer is not necessarily willing to inline an unsafe perform IO computation. That being said, there is another version of unsafe perform IO called unsafe inline perform IO, which is even more magical. And what that basically says is, actually, I'm okay with the optimizer doing whatever the heck it normally does with this operation, and my guarantees on what actually happens in that case can be reduced. So actually, there's basically a sliding scale of unsafety. Unsafe perform IO, yeah, it's pretty unsafe. You can segfault Haskell with that, and it's kind of crazy, and you shouldn't use it. But we will actually give relatively stringent guarantees that it doesn't get duplicated, it doesn't get inlined. But then if you want it to get duplicated because you're like trying to squeeze out every last bit of performance, there's unsafe inline IO, there's unsafe dupable IO that says you can duplicate the computation. So it's kind of crazy. And yes, you do need to actually know how the runtime system is implemented to make use of these effectively. So this is like very, very like random trivia, but hey, now you know. Okay, in my last 7 minutes, I want to tell you about occurrences of lazy evaluation in other languages. And in particular, I said I was going to talk about generators. So what is a generator? So generators in Python are a language feature that make it easier to write computations that are incremental in some sense. So here is a function that is a generator for natural numbers. So what does it do? So it sets I to be 0, and then in an infinite loop, it yields an I, and then increments I by 1. What the heck is this yield? This yield essentially says, hey, there's some function calling nats. In fact, there's some function that's iterating over the list that nats is generating. So when I hit a yield statement, I am going to go ahead and return that value immediately to the calling context. The calling context is going to go ahead and do some stuff with it. And then only when it returns to iterating on nats do I continue executing the rest of this program. So in other words, yield suspends execution until the next item in the generator is requested. So with generators, you can implement things that are like streams, and indeed many Haskell idioms work. So there are many Haskell programs that sort of work with lazy evaluation, and you could port them into Python using generators instead. However, there's one very, very important caveat. Python is an imperative programming language, and in imperative programming language, we have mutable state, and generators are implemented also as mutable state. And what that means is once you have finished running through a generator, that's it. You're done. The generator's done. There's no way to go back to the earlier values in the generator. So range by default is a generator, and I can assign the range generator to an object. And if I loop over it once, I will get all the elements that I expected in the range. But if I loop over it again, I'll print nothing, because at that point the generator has been exhausted, and it's not like Haskell where if I had written similar looking code, the list would have materialized into a size 10 list and I could reuse it later. Which one is better? It's a little hard to say. The Python version can result in confusing behavior if you were expecting a list and got a generator instead. However, it does have the benefit that you don't hold on to data too long. In Haskell, one of the things that makes it a little hard for people to understand why their program is using up so much memory is because you might have this lazy structure. And originally, before you had inflated it, it was very small. And then you went ahead and evaluated a bunch, and now you have 100,000 length lazy structure. And if you're still holding on to that head of this list, it's still taking up that 100,000 elements that you computed, even if maybe it was very cheap to compute those elements and you didn't want to hold on to them. You just wanted to throw it out and recompute it later if that was the case. You have to be careful. By default, Haskell will just hold on to everything because that's what you said, right? You defined a list with this many elements, and Haskell didn't materialize it to begin with, but then later started materializing it. So people often say that Haskell, it's hard to make sure your programs don't use too much space because of lazy evaluation. But this isn't strictly true. Because often you can fix the problem by being even more lazy in your program. So it's more of you just have to understand how the things are put together and then, actually write the computation that corresponds to the usage pattern that makes sense for your application. And because people aren't used to programming in a lazily evaluated language, that can be a little confusing. But Haskell makes it very simple to write lazy programs. And so if you really if you're ever working on a system which is lazy evaluated, and this totally happens. In fact, there's lots of really interesting research on so-called incremental languages where it's a step up from lazy evaluation. So lazy evaluation says we don't bother evaluating things until we need them. Incremental computation says we don't even bother evaluating things if they're the same as what we evaluated them to the last time we executed them. And if you want to understand the performance characteristics of these systems, it's actually pretty nice to have written a bunch of Haskell because it'll give you a bunch of intuitions about what types of things can go wrong. Okay, 1 minute left. Any more questions before we wrap it up for today? All right. Thanks everyone for coming. The homework for this will be posted fairly shortly, probably tonight. It's already in PL Class Public, so if you want to get started. And yeah, see you all on Wednesday. Cheers.